Hi, I'm Mark Barsamian. In this video, I'll introduce a new derivative rule called the chain rule, and I'll apply the chain rule to problems involving a function that has an outer function that is a power function. This material is from section 3.4 of the book, more specifically page 204 to the middle of page 210, examples 1, 2, 3, and 4a. The corresponding homework is this collection of exercises from section 3.4. Before starting, let's recall our derivative rules. This batch of rules from section 2.5, the constant function rule, power rule, sum, and constant multiple rule. This batch of rules from section 3.2 for finding the derivatives of exponential functions of various types and logarithmic functions. The derivative rules from section 3.3, the product rule and quotient rule. So in this video, we'll learn how to take the derivative of what's called a composition of functions, that is, functions of this form. F of x is some outer function with some inner function inside of it. So you could call this a nested function. The rule that we will use is called the chain rule, and it goes as follows. If f of x is one of those compositions of functions, a nested function, outer parentheses, inner parentheses x, then its derivative, f prime, is written outer prime parentheses, inner parentheses x times inner prime parentheses x. In single equation form, we have this. The derivative of one of those nested functions is this expression. Now that's a kind of strange looking notation, but it's actually descriptive and will become clearer if we do some examples. In the examples today, we'll be considering functions where the outer function is a power function. The book solves these using what it calls the general power rule. That's simply a special case of the chain rule, and it's completely unnecessary to have a rule that's a particular case of the chain rule. So in this video, I'll just simply use the chain rule, and when you apply the chain rule to problems where the outer function is a power function, it works as the book's so-called general power rule works. It just gives you one less thing to remember. You just simply remember the chain rule. Our first example, let f of x be this function. Find f prime of x. Okay, I'm going to take an approach that will be the same approach that I will use for all of the chain rule problems. And it's the same starting approach that I use in all of the problems that I do where I compute a derivative. I start by writing what we're going to be computing. Now, today is a big day. We learn about the chain rule, but remember, every time we've learned a new derivative rule, we have acknowledged that we keep using our earlier derivative rules. So the first derivative rule that we use here is not the chain rule. It's going to be the constant multiple rule. We have a constant multiple, this number 2, so we address that first. Now, notice here we have a nested function, a composition of functions. We have an outer function with this pair of parentheses with an exponent 7, and then sitting inside that pair of parentheses, we have another whole function. So this is a case where we'll use the chain rule. Now let's go back and look at how the chain rule looks. The chain rule says the derivative of one of these things is this. Well, I find it helpful in the early examples to actually write this form to help us get a handle on how to use this form. What I mean by that is this. So I'm just simply replacing our function with this generic form. I replaced our function with that. we're introducing these new things, this inner parentheses x and this thing called outer. So I'll do an official introduction over here on the side, and I'll do it in what I call the chain rule details box. So there is what I'm calling inner parentheses x. It's just the thing that's inside the parentheses. Now I'm going to introduce the outer function. Notice that I have not included a variable here. The outer function I want to think of as just those parentheses. It's actually helpful to not use a variable when describing the outer function. So I've used this idea before in this course. I would refer to this as the empty version of the outer function. Now notice about this outer function. This outer function is a power function. Remember that the subject for today is examples where the outer function is a power function. So here we have an example of an outer function that's a power function. Now where do we go from here? Well, we use the chain rule. Let's go back up and look at the chain rule. There's the chain rule. It says that we can replace one of these with one of these. So let's go do that. So there we've used the chain rule. Now the chain rule is telling us what we need to do. We need to get all of these things and assemble them according to this prescription. Well, we get those things ready over here in the chain rule details box. So we've got our inner parentheses x, that's going to go there. But we need these other things. We need inner prime parentheses x, and we need outer prime. Well, inner prime parentheses x is easy enough. Now I'm just going to skip right to the result. So that's our inner prime parentheses x. Now we need outer prime. According to these instructions, we need the derivative of the outer function. Well, remember that the outer function that I've presented is an empty function. It's the empty version of it. The outer function is parentheses to the seventh. Well, how do you find the derivative of parentheses to the seventh? Well, the idea is just think about this if it had a variable. If the outer function was x to the seventh, its derivative would be 7x to the sixth. If the outer function was t to the seventh, then its derivative would be 7 times t to the sixth. Well, our outer function is parentheses to the seventh, so its derivative is 7 times parentheses to the sixth. So the derivative of the outer function is also an empty function. So this green box is off to the side. It's called the chain rule details box, and it's where I get all the things ready to populate this expression. So now we assemble those terms from the chain rule details box. So there's my outer prime. Now according to these instructions, I'm supposed to stuff those parentheses with the inner function. So that's up here. And then I have to multiply by inner prime parentheses x. Well, inner prime parentheses x is sitting here. Now notice what I did there. It looks like I did exactly what was asked of me. These instructions said that I need to multiply by inner prime of x. So there's my dot, and there's my inner prime of x. But what I've written is actually incorrect. What I was supposed to do is multiply all of this stuff by the inner prime function. What I did actually, according to what I wrote, though, is I only multiplied it by that one term. According to order of operations, that multiplication happens before that addition. So what I've written here is actually wrong. I have to include parentheses. If I don't include those parentheses, then what I've written is wrong. Now we can clean this up a little bit. We can combine these two constants that are sitting in front. into a single constant. And there's our answer. That's our f prime of x. Let's go on and do another example. Example 2. Let f of x be this function. Find f prime of x. Notice that this function is presented as a quotient. Remember that we have a rule for finding the derivatives of quotients. It's a really ugly rule. The derivative of a quotient is computed by this crazy formula. And also look what's in the denominator of that quotient. We have a nested function. So this looks like a quotient rule problem that's also going to require the chain rule to find the derivative of the denominator. Well, so that's really hard. But notice that we can rewrite the function so that it's not a quotient. So we're going to rewrite the function in power function form. This function is presented in positive exponent form. That exponent 7 is a positive number. But this function will be much more convenient for finding the derivative if we rewrite the function in power function form. Now we have our function in power function form, we're ready to find the derivative. So there we've applied the constant multiple rule, and look, we now have the derivative of a nested function. So I'll do what I did in the previous problem. I'll introduce the form that we will recognize as the form of a composition of functions, and then I'll show how the chain rule tells us to deal with it. So there you see we recognize the form, and we do what the chain rule says to do. We replace that red circled stuff with this red circled stuff. And we do the details over in a chain rule details box. So there's our chain rule details box. I computed inner prime because I know I'm going to need one of those there. I identified the outer function, and it's an empty version of the outer function, parentheses to the minus 7. And then we knew that we were going to need outer prime, so I computed outer prime. And I used the power rule. Here I should point out again that this outer function is a power function. Remember, the subject for today is chain rule problems where the outer function is a power function. So I used the power rule to compute the derivative of the outer function. And notice I did not try to do this exponent calculation in my head. I just wrote down what the power rule says. The new exponent is going to be minus 7 minus 1. I'm going to write that down on the page, and then in the next step, compute that. I get minus 8. If you try to do that work in your head, a common mistake will be that students will use the power rule, and they'll say that the derivative is minus 7x to the minus 6th. They'll just lower the exponent by 1 in their head. But if you write, and that would be incorrect. If you write the exponent down as I've done, you actually write down the computation. It's going to be minus 7 minus 1. You write that on paper, you're less inclined to make that mistake. You'll get the correct exponent more reliably. Now notice that at this point, we've found the derivative of the outer function. But it's better to rewrite it into positive exponent form. We started with a function in positive exponent form. We put it into power function form because that's a more convenient form for finding the derivative. Once you find the derivative, though, it's good to put the function back into positive exponent form. So we found the derivative here, and we went a couple more steps to rewrite it in positive exponent form. Okay, there we've got all the parts we need to assemble this expression. So there's my outer prime as requested there, and you can see I'm supposed to stuff those parentheses with the original inner function. So I get that here. And then what's next? Well, according to these instructions, I'm going to multiply by inner prime parentheses x. Now I have to be careful. I have a fraction here, and I'm multiplying it by something that's not a fraction. So I have to make sure that I write the inner prime up on the baseline, not down on the floor. So I did not put that stuff down on the floor with the parentheses to the 8th. And furthermore, I've got to be careful and put that stuff in parentheses. Now I can simplify this. I combined these two constants into this single constant. I wrote this all as a single fraction. But notice that I can simplify some more. Notice that in these parentheses, both terms contain a 2x. So I'm going to factor out a 2x. And there's our derivative. I factored out a 2x, so instead of a minus 14, I have a minus 28x. And before going on, notice that the structure of this problem was exactly like the structure of the previous problem. I mean, if you squint your eyes, that solution looks just like this solution. Every step is the same approach. The only difference is the particular power function that I found for my outer function. Other than that, everything is the same. Let's go on to example 3. In example 3, f of x is this function. We have to find f prime of x. Well, just as in the previous problem, we took the given form of f of x and we rewrote it in power function form because that's more convenient for finding the derivative. We'll do that in this problem as well. So our function was presented in radical form. It's more convenient to have it in power function form for the purpose of finding the derivative. Now we find the derivative. So we use the constant multiple rule. Now we do what we did in the previous two problems. We recognize the form of the chain rule. And as we have done in the previous two problems, we do the details over in a green chain rule details box. So there's our outer function, and it's worth reminding us again that this is a power function. The subject for today is chain rule problems where the outer function is a power function. And of course, this is the empty version of the outer function. Since the outer function is a power function, we find its derivative using the power rule. So there's our derivative. I have not done the exponent calculation in my head. I just wrote it down. Now I'll actually compute the exponent and simplify this until it's in a convenient positive exponent form. And once we have it in positive exponent form, we realize it might even be nicer to put it in radical form. Our original function was in radical form. So there's a great big chain rule details box. And we now can just use those pieces in that box to assemble that expression. There's my outer prime. Forgot the 2 there. Now I'm supposed to stuff these parentheses with the inner function, which is sitting here. Then I'm supposed to multiply by inner prime, and I've got to be careful because I have a fraction here, so I want to write the inner prime in a way that it's multiplying the fraction, so it needs to be up on the baseline, not down on the floor. My inner prime is sitting over here. So there you can see that I've written the inner prime up on the baseline, not on the floor, and also I've got to use parentheses. Now I can clean this up. And there's our derivative. And again, you can see that the form of this solution, the structure, is exactly the same as the structure from the previous 2 problems. All 3 of these examples use the same structure. Now this is actually just question A. There's more. Question B is find the equation of the line tangent to the graph of f of x at x equals 4. Well, remember that we approach these tangent line problems the same way every time we do one. We start by writing down what we are going to do. So we need to build this equation. We should remind ourselves what this is. That's the point-slope form of the equation of the tangent line. And we will do next what we always do. We get parts. We have 3 things we need to get. A, f of A, f prime of A. A is the x-coordinate of the point of tangency. Well, we're given that. It's the number 4. F of A is the y-coordinate of the point of tangency. Of course, our value of A is the number 4. And what that expression means is to substitute 4 into the formula for f of x. Now here it's important to keep track of which function we're talking about, because now we're talking about 2 functions. We have this function, f of x, and we have this function, f prime of x. So when we're talking about substituting things into equations or functions, we need to make sure that we use the correct function. This symbol means we substitute x equals 4 into the formula for f of x. So let's remind ourselves what that formula is. It's that, 3 times square root of x squared minus 3x plus 21. So we end up with f parentheses a equals 15. And remember, that's the y-coordinate of the point of tangency. All right, our last part that we need to get is f prime parentheses a. And of course that means f prime parentheses 4, because our value of a is a equals 4. And remember what this means. It means that we substitute x equals 4 into the formula for f prime. This does not mean to find the derivative of 4. The derivative of 4 would be the number 0. That symbol there means to substitute x equals 4 into the formula for f prime of x. Now let's remind ourselves what the formula for f prime of x is. It's that thing. So let's write that formula down on the next page. And then let's substitute x equals 4 into that formula. Now we can skip ahead a little bit here. We know that this square root expression is just the number 5. So I can skip some of those steps here. I should make this multiplication a little bit clearer over here on the right, 3.5. Okay, so in this expression we're going to have 3 times the quantity 8 minus 3 over 2 times 5. So we get f prime parentheses a equals 3/2. And remember what this is. This is the slope of the tangent line. So we found our derivative, and we found the parts. Now we have to substitute our parts into the tangent line equation. So we have to substitute a equals 4 there. We have to substitute f of a equals 15 there. We have to substitute f prime parentheses a, which is the number 3/2, there. And there's our equation that's the point slope form of the equation of the tangent line. Now we should convert this to slope-intercept form by solving for y. And we end up with this equation. Y equals 3/2 x plus 9. That's another presentation of the equation of the tangent line. That's the slope-intercept form of the equation of the tangent line. Let's go on. Question C says, find the x-coordinates of all points on the graph of f of x that have horizontal tangent lines. So here it's important to remember the connection. We're talking about horizontal tangent lines. That means lines that have slope m equals 0. The connection you've got to make is that the slope of the tangent line at some point is equal to the value of the derivative at that point. So there's the important connection. The slope of the line tangent to the graph of f of x at x equals c equals f prime parentheses c. So we're trying to find the numbers c that will cause this to happen. We're looking for the numbers x equals c such that f prime parentheses c equals 0. So the strategy is set f prime of x equal to 0 and solve for x. So there's our derivative, and we have to find the values of x that cause that derivative to be 0. Well, here it's very important to remember a basic thing about solving equations. We have a fraction that's got to be equal to 0. Well, remember that a fraction can only be 0 in one situation. A fraction is only 0 when the numerator is 0 and the denominator is not 0. So as ugly as this expression is, all we need to do is figure out where are the places where the numerator is 0 and the denominator is not 0. Well, the numerator is fairly simple. Let's start by finding all the places where the numerator is 0. We see that x equals 3/2. So that's the only x value that's a candidate for an x value that would cause this equation to be true. That's an x value that causes the numerator to be 0. but we have to double check to make sure that the denominator is not 0 when x is 3/2. So we have to check the denominator, so here we go. So this arithmetic is not crazy hard, but it's a nuisance. 3/2 squared is 9/4. 3 times 3/2 is 9/2. 9/4 minus 9/2, well, that's the same as 9/4 minus 18/4, so I end up with minus 9/4. Minus 9/4 plus 21 is minus 9/4 plus 84/4, so that's 75/4. So this just seems awfully hard. What on earth is 75/4? What's the square root of that? It seems really hard. Well, remember, all we care about is the denominator non-zero? So at this point, we realize, oh, we're taking the square root of a number that's not 0, and so we're going to get a number that's not 0. So our conclusion is the x values where the graph has a horizontal tangent line is just x equals 3/2. So we can make our conclusion clearer. So our conclusion is that there's a horizontal tangent line at x equals 3/2 because f prime of x equals 0 there. Okay, question D, illustrate the results from B and C on this given graph. Well, question C we just did. We found that there's a horizontal tangent line at x equals 3/2, so we can draw that. Let's see. So the point on the graph where x equals 3/2 is here, and we need to illustrate the tangent line. The tangent line has this equation, y equals 3/2 x plus 9. So it has a y-intercept at 9, and what else? Well, it goes through the point of tangency. Point of tangency, remember, has x-coordinate 4 and y-coordinate 15. So we should put the point 4, 15 on the graph. And remember the y-intercept on the tangent line. The y-intercept is at 0, 9. So we just have to connect those 2 points. And notice again, I labeled the tangent line with its equation. And remember, when writing expressions like this, where you have a fraction sitting next to something that's not a fraction, put the fraction in parentheses. And the thing next to it that's not a fraction, be sure to not write it on the floor. Write it up on the baseline. And we should be sure to label this graph for what it is. It's the graph of the function f of x. So there's our equation for the function, and there is our result from question B illustrated. We drew that tangent line and we labeled its important features, the xy coordinates of the point of tangency, the y-intercept, the equation of the tangent line. And there's our illustration of the result of question C. We drew a horizontal tangent line at x equals 3/2. That's the end of that example, and that's the end of the video.